Já estamos lá, já. So, hello everyone. We are going to have the next presentation. Is Sabrina will talk about cosmology, and she'll talk about the expansion of the universe and some important equations for cosmology, like the Friedmann equations and the Boltzmann equation. What? Sorry?
Não sabe se os slides?
Na universidade de José Carlos, mais difícil.
Okay. So, okay.
So, hi to everyone. Today I'm going to talk a little about the chapter 2 and 3 of the Dawdson and the Smith book that is about modern cosmology. So I will talk a little about the metric, the general relativity, and the Boltzmann equation, the Friedmann equation, the Einstein equation. So in the second chapter, we're gonna introduce the expanding universe, the idea of the expanding universe. So to talk about the expanding universe, we need to talk about the metric that is related with the general relativity and the constituents of the universe that are related with the statistical mechanics. So I'm going to talk about these two concepts that we need to understand the expanding of the universe. So first, we have the metric. So we can make a relation with the metric with for example, the Einstein equation. The Einstein equation have the metric inside it. So the metric can, for example, try to connect the geometry of the space-time with the distribution of matter and the energy. So the metric can too be used to measure the distance between 2 points in the space-time and to make some predictions for the expanding universe. So here I have two examples of metric. So here I have a metric where I am considering the Cartesian coordinates. So this is a matrix identity. And this is a metric where I'm considering the polar coordinates. So this will depend on the area square. So this metric depends on the coordinate system, but the quantity that the metric can measure, that is the distance, doesn't depend on the coordinate system. This is invariant, but these quantities will depend on the metric. So here I have another two examples of metric. For the spatial relativity, I have no curvature. So my metric is given by the Minkowski's metric. So it's given by this. And if we consider an universe that is expanding, we can consider this metric that is the Friedmann-Lemaitre Robertson-Walker metric. And the difference between this metric and this metric is that this metric has the scale factor that we use to try to measure the expansion of the universe. So this is the difference. So this is what we have about metric. So when we are considering a curved space-time, we are considering basically the shortest path between 2 points. So we can measure this using the geodesic. And the geodesic is basically a path that a particle do between a point and another point. It's the shorter path. So we have this equation here that is the equation for this geodesic. So with this equation, I can try to solve this to try to find a path for a particle that is moving in some arbitrary space. But this symbol here is the Christoffel symbol, and it depends on the metric. So we need to choose a specific space with a specific metric, so we can calculate the path of this particle for that specific space. So if my space is flat, for example, the distance between two paths is it's a straight line. But if my space is curved, the distance between two paths is a geodesy. So we have the metric here too. Another topic, it's about the constituents of the universe. So if we want to talk about some components of the universe like matter and radiation, we need to talk about the pressure and the energy density. There are some components, there are some quantities that characterize these quantities. So if we talk about pressure and energy density, we can relate this with this parameter. That is the parameter for the state equation. So here we have it's just a fraction between the pressure that we have for some component and the density that we have for some component, the energy density. So we can use this to try to explain an universe that is dominated by some specific element, by some specific component. So here I can find to the relativistic tensor that would depend on this energy density and on the pressure. And with this tensor, I can find a conservation law. That is like a generalization of the continuity equation and the Euler equation. So here I have a covariant derivative, and this will act on this tensor, that is our energy momentum tensor, and this is equal 0. This is a conservation law, and if we use this conservation law, we can find for some specific metric. It's like an equation of the evolution of the energy density and the pressure for some components of the universe, like the matter and radiation. So how I put here, this will explain how the matter and radiation behave for the expansion. So in the chapter, I forgot one thing. We can express the pressure and the density in terms of a distribution function. So this can make like a connection between macroscopical properties with the microscopical properties. So this will be important in the chapter 3, because in chapter 3, I will talk about the fundamental equations of cosmology. So basically in cosmology, we can think of cosmology like an application of the general relativity and coupled with the statistical mechanics. So for example, when we are talking about cosmology, we are talking about not just single particles, but a collection of particles. And the main force that we are considering in cosmology is the gravity. So we can use two equations to try to derive all the results for cosmology. That is the Einstein equation, and that is the Boltzmann equation. So for the Einstein equation, for example, I have this, that is the Einstein tensor. This is related to the geometry of space-time. This is the lambda, is our cosmological constant, and this is the metric that I talk about. This is the tensor of energy momentum that is related to the matter of the space. So here we have a relation of the geometry of the space-time with the distribution of the matter and energy in that space. So, for example, the Einstein tensor, it is defined by the Ricci tensor and by the Ricci scalar. But the Ricci tensor is related to the Christoffel symbol. And the Christoffel symbol, it is related with the metric. So if we want to derive the Einstein equation, we need to know the metric of our space. So here is an example. If we use this metric of the Friedmann metric, we can find the Friedmann equation, that is like our Einstein equation for that metric. So in that metric, we are considering the universe homogeneous, isotropic, and that is flat. So that is Euclidean. This means that it has no curvature. So if we use this metric, we can find our freedom equation that we talk about the expansion rate of the universe. So this expression basically talk that the expansion of the universe, that the expansion rate of the universe, it depends on the density parameter that is associated with the components of the universe, and with the curvature parameter that it is associated with the curvature of the universe. So in this case of a universe that has no curvature, this is vanished, this is equal to 0. So we have just this term. So this basically says that we can connect the expansion rate of the universe with the components of the universe and with the parameter curvature. So when we want to talk about matter and radiation, we need to understand the behavior of the average behavior of the collections of particles. So we need to use a function that we call the distribution function that is defined by this expression here. So this depends on the momentum and the position and on the time. So we need to define this in a phase space. And basically this function can give us some macroscopical properties about the matter and radiation, for example. So we use the Boltzmann equation to try to explain how this distribution function will evolve with the time. So we need first to set a number of particles that is basically given by this expression that is proportional to the distribution function. And we can imagine that we have a number of particles inside a small volume of the phase space. And like if this number of particles is conserved, we have this equation for the distribution function. But if this is not conserved, if we had a change of number of particles inside a certain volume of the phase space to another, if we have this change, we have these equations of motion for the distribution function. So here we have a collision terms that will consider a particle-particle interactions. That is basically a direct interaction particle that can be like in annihilation and in scattering. So, or in pair creation. So we have this equation that can explain how the distribution function will change with the interactions of particles. So this is called collision term. So if we choose a specific metric, we can find, for example, the Boltzmann equation for the expanding universe, and we can consider two specific limits like the non-relativistic and the relativistic. So for the relativistic, we can find the behavior of the distribution function for neutrinos and photons, for example. So, well, what I talked about was about the Boltzmann equation and the Einstein equation, but I don't consider perturbations. So when we consider perturbations, so we are considering a perturbated space-time, we need to define two new functions. This function, C, that is the Newtonian, that is like a Newtonian potential that can be used to explain how non-relativistic bodies moving in the space. So this is for slow motion. And we can define this other function here that is for a perturbation, a spatial curvature. we are considering a perturbation in the spatial curvature. So we can find like the scale factor perturbed with this function. And if we are in a perturbated space-time, we need to define the metric accordingly with these functions. So accordingly with the Newtonian potential and the function for spatial curvature. So we need to define this new metric here. And we are considering just terms of linear order because this is not a big value for the perturbation. So we just consider it the linear order. And if we want, for example, to finish, if we want to derive the Boltzmann equation and the Einstein equation, we need to use this metric for a perturbated space-time. In the book, he will do this in the chapter 6. He talks. So, okay. So, how about?
Questions?
Actually, I have two questions. You said in the beginning of your presentation that two hypotheses are really important, that the hypothesis of homogeneity and isotropy. Do you understand more or less what is isotropy and what is homogeneity of the universe?
Isotropy is like we have the same things in all directions, and the homogeneity is like we have the same thing in all the points.
Do you realize how the universe is? Because this is a general idea, but the first time I heard about this isotropy and homogeneity of the universe, it's really complex because if you say, for example, that you are looking at in the sun and to other direction, in principle, you have not isotropic universe. So, I mean, it's a really hard question because you said about homogeneity in the end. I mean, but this idea of homogeneity and isotropy, you need to think at big scale.
Large scale.
Right? In big scales, the universe looks like the same. But at small scales, you have some difference. Because this idea is really hard to catch. The first time you heard it, you start to think about the universe. So that is just why I asked you.
What is that? I don't believe it. So I mean, so let's just explain to her what it is. So exactly. So you're going to ask a question. So if you're just talking about homogeneity and isotropy, do you know what evidence of experimental observation that we have that points to us that we should have at large scales a universe that is homogeneous and isotropic? Do you know any evidence that supports this claim?
CMB is like
Certainly it's spectrum. That's it. Like you have small, little homogeneities, but at large scales you have exactly what you just explained. And large scale structures.
large scale structure.
So you look at galaxies very far away, they need to be homogeneous and isotropic.
Cosmology, CMB is a joker.
Mm.
Every question someone asks what evidence you can throw that card.
Very likely you're gonna get it right.
What's the first thing that I think?
But it's correct. Yeah, that's it. That's the question.
But did you get the difference between the two?
Yes. One is for direction and the other is for the points, but this is in large scale.
Is this one is rotation, one is translation. Okay, awesome. Okay, so now let's go to vortices. Uma informação que eu gostaria de dar a todos vocês, também para vocês entenderem, é que para os novatos, né? Seria bom que faz um bom tempo, agora a gente vai fazer esse novo quando o Davi chegar, Davi, um podólogo que vem da Colômbia, vai chegar dia 6 de junho. Quando ele chegar, ele vai estar...
Muito obrigado, pessoal. Até mais.
Então, para chegar no office, a gente sabe, para vocês entenderem os novatos,